All right, so section 7.2 is going to be measuring the quality of a survey. So when we're measuring the quality of a survey, what science is all about is the ability to replicate, right? So we're not looking at just the one survey we do, we're looking at what if we did the survey over and over and over again when we get the same results. So when we're looking at a survey, we're going to be talking about two main ideas. One is precision and the other one is accuracy. So what we have here, we have golf balls, okay, and we're trying to get them in the hole. And on the first one, what we have is that we have a survey that is both precise and accurate. So what that means, if we look at this, is each golf ball represents a survey, and the hole represents the actual population. Okay, so if we repeat a survey over and over and over again with a different sample, what we want is that we would like that all of our samples are relatively similar, close together, and they're close to the population. Now, if we look at B, what we see is that all of our surveys and samples, so remember again, this is a sample using a survey method, all of our samples are close together, but they're not actually close to the whole or the population. Now, on part C, what we could see is that it's not precise, but it is accurate. So what that means is that our samples are all kind of wonky, like they're not close to each other, but if you look at this, you can kind of see that they are aimed towards the population. Here on part D, this isn't precise or accurate. So my golf balls aren't close to each other, right? Like in part D, they were kind of grouped together. Okay, not only are they not close to each other, it looks like they were almost like trying to hit this imaginary hole over here, and they're missing the actual population. Okay, so in this metaphor, again, the cup represents our population, and each ball represents a sample. Okay? So, the closer together the balls are together, the better we get a better precision measurement. But the closer the balls are to the hole, the more accurate we are. So what accuracy is it's when we're moving in the right direction of the true population parameter, okay? And the way that we check that we're doing this right is that we measure it using something called bias. So just remember that accuracy is related to bias. Now precision is if we repeat the survey over and over and over, are we going to get around the same numbers? So precision is related to standard error, okay? This is a really big deal. You guys are going to have to know that for your final exam, so just keep that under your hat. Now, for this next example, all right, so let's say that we want to know the percentage of females taking college courses, okay? First, we want to look at a sampling method that would have poor accuracy, and then we want to look at one that would have poor precision. So let's go ahead and look back up and see what poor accuracy would be. So accuracy would mean that we would be looking at something that's biased. So let's say that the true population proportion of women taking college courses is 60%. Okay, so a method that might lead us to have poor accuracy is if we only surveyed let's say that we only surveyed nursing courses. Okay, nursing courses would give us a lot of females. So if we only surveyed nursing courses, let's say that one nursing course we looked at had so this would be for my sample, had about 80% female, and I did this over and over and over, and my survey kept having 80% females. Some of them would have more females, some of them would have less females. What would happen is that if I drew a histogram, or not a histogram, yeah, a histogram, but a distribution relating to my sampling survey, what would happen is that all my samples would be greater than the population, which would make it biased. Okay, now let's look at an example where we have poor accuracy, or I'm sorry, poor precision. So again, the actual population is 60% female. Okay, now let's look at one that had poor precision. So let's think of classes that not everybody has to take, right? So let's say that we survey occupational specific courses only. So what would happen is that we would look at a nursing class, and that would tell us that we had 80% of registered females. And then let's say that we looked at a mechanical engineering class, and let's say that that only had 40%. Okay, so what would happen is that we would have all of these different surveys, and they would keep bouncing back and forth, and a lot of them wouldn't even be close to each other. But if we average them out, we'd probably get pretty close to the actual population, but all of our surveys would give us dramatically different results, right? So if we surveyed only occupational specific courses, we would get numbers that went all over the place. All right, so now what we're going to do is that we are going to look at a simulation that's going to tell us the behavior of estimators. Another way to talk about estimators is calling them samples. So here's what we're going to do is we are going to run 3 separate simulations in order to observe accuracy and precision and how we can improve them. Okay? So in the first simulation, what we're going to have is we are going to have a very small population, so we're only going to have 8 people, and then our sample size is only going to be size 4. Then we're going to slowly increase the size of the population and the size of the sample. And in the third one, we're going to keep this population the same but increase the sample. And what we want to know is, how does increasing the sample proportion change what we see for the population proportion? Or, yes, that's right. So in the first simulation, we are going to look at a population of 8 people, and some are dog people and some are cat people, and they're labeled below. So what we've done is that we've taken these 8 people and we've coded them 1 through 8, and we have person 1 and person 2 are cat people, and then 3 through 8 are dog people. So we have P is 2 out of 8, which is 25%. So 25% of our population are cat people. Now what we want to do is that we want to randomly pull 4 individuals from this population. Okay? We're going to do it over and over again, and let's see what could happen. So there are actually 70 different ways to pick 4 people from the set of 8, and they're listed right here. So just to recall, if we have the sample group and we randomly pull person 1, 2, 4, and 8, this would translate to a cat, cat, dog, dog person, and our sample would tell us that there were 50% cat people, but the actual population would be 25%. So of all the 70 different ways there are to pull a sample, 15 of them are going to result in 50% cat people. Okay, so these yellow ones right here, these 15 are going to result in 50% cat people. Okay, so we have 15 out of 70. 15 ways in which our set of 4 contains no cat people, so that would be these green over here. And 40 in which our set of 4 contains 25% cat people, so 40 out of 70. Okay? So, here's the deal, is that we have 2 different ways where we can get what we refer to as kind of a bad sample, right? So, if we get this sample, that's not good, because that tells us, hey, did you know that 50% of people are cat people? Well, that's not true. 25% are cat people. Also, we could get this one that says, hey, did you know that nobody's a cat person? And that's not true either, because we have 25% again. However, this last one, hey, there's 40 ways in which we can get a set of 4 that contains 25% cat people. That's good, because that would be a good representation of the actual population. So, the probability that our sample would have 0 cat people is roughly, I'm just going to round to 2 decimal places, is about 21.43%. So that's the 15 out of 70. Okay. The probability that our sample size has 4 that has 50% is the same one. It's 21.43%. And the probability that our sample of 4 has 25% cat people is going to be 57.41%. So what does this mean? Well, if we drew a histogram with all our possible samplings, which is called the sampling distribution, here's what that would look like. Is the probability that we get 0%, okay, remember that's about 21%. Probability we see 25% is 57-ish, and 50% is this. So, what this means is that there is a probability that we're going to get a bad sample, but we have a high probability that our sample is going to be the same as our population, which is wonderful. Okay, so yeah, you might get a bad sample, but overall, most of your samples are going to represent your population. So, if we just randomly picked 3 different samples and looked at them, so for example, our first sample would be person 6, 8, 4, and 5, which would be all dog people, which means we'd have 0% cat people. Our second one is 7, 2, 6, 3, so it'd be dog, cat, dog, dog. Okay? And our third one is cat, dog, 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 which would be 25%. Here's what we learned. Are our estimators, p hat, and our parameters p always the same? No, our sample does not always equal our population. Something I want to point out to you guys is notice that the population always stays the same. It's our sample that can change. Now, if we look at the mean of the sampling distribution, okay, remember what the mean is that's going to be the center if you have a symmetric graph. So if we look back up here, well, the mean, or the most common value that we would see, is 25%. So like we said, the 25% is the mean of the sampling distribution, and it is also p. What this means is that if we repeat the survey over and over and over again, we're very likely to see the same results. That will match the population. So another thing that we want to know is what's the bias of the survey? So the bias is the difference between the mean of our estimator and the mean of our population. So in this case, since this is 25% and this is 25%, then our bias equals 0. The reason our bias is 0 is because we didn't do anything that would have skewed our results. We didn't just go to dog parks and we didn't just go to cat cafes, right? We did a lot of random sampling. The precision of a survey, okay, so how we measure precision is reflected in the spread of the sampling distribution. And we measure it using our old friend standard deviation. Okay, so in this case, the standard deviation, or the precision of the sampling distribution, is about 16%. We're going to learn how to find this later by hand. It's actually much easier than finding the standard deviation. And it has a special name. Here's the special name. So remember, we're looking at how far off our samples are from our population, not how far off an individual is from a sample. So instead of calling it the standard deviation, we call it the standard, how far off we are from the population, standard error. Okay, so we're going to stop here. I'm going to go ahead and pop over to another video, and then we're going to continue on with simulation 2 and 3.